Okay, good morning to everyone. You have just finished the rectangular components of a force in the two-dimensional force systems. Now let us now proceed to the rectangular components of a force in three dimensions. Now, so if you try to imagine that this is a box, then you have the x-axis, the y-axis, and we now have the z-axis. Now, let us try to consider that the force is acting from the origin of the coordinate system to such direction, and this is therefore the vector F. Okay, you try to take note that vector in your handouts are written in bold-faced letter. Those that are not written in bold-faced letter are the magnitude of that corresponding vector. So, first, if this now the vector F, now, so we now have the corresponding component in the x-axis such that this is now your f of x. And your f of x and the vector f makes an angle of theta x, okay, with the x-axis. It makes an angle of theta x with the x-axis. And therefore, the rectangular component of that vector in the x-axis is now equal to f multiply this one by cosine of theta x. Similarly, if this one in here is now the vector f, so this is the component of the force in the y-axis, and the force or the vector f is making an angle of theta y, okay, in the y-axis, then the component of the vector in the y direction or y-axis is equal to f cosine of theta y. Now, similarly, the component of the vector f in the z-axis, which makes an angle of theta z with z-axis, then the component fz is now equal to, f. We now have cosine of theta z. So these are therefore the components. Now, if we know the rectangular components of this force F, then we can determine now the magnitude of the vector F, and the magnitude of the vector F is now equal to the square root of f of x squared plus f of y squared plus f sub z squared. Okay, so your f of x is f cosine of theta x, your f of y is equal to f cosine of theta y, and your f sub z is equal to f cosine of theta z. Now, let us try to determine now the angle that the vector f makes with the horizontal, makes with the coordinate axis. Okay, so we now have your theta x is now equal to the arc cosine of, so this is equal to the arc cosine of the component of that vector in the x-axis all over the magnitude of the vector f. Okay, all over the magnitude of the vector f. So that is now the arc cosine of fx all over the magnitude of f. Now, your theta y is now equal to the arc cosine of f sub y all over the magnitude of the vector f, and your theta z is now equal to the arc cosine of f sub z all over F. So f sub z all over f. Okay. So knowing now the angle, this theta x, we have now your theta y, and theta z is therefore known as the direction cosine of the force. So that is the direction angle or direction cosine of the force. Okay, direction cosine of the force. Now, and you try to take note that this equation, okay, the cosine of this angle must satisfy the equation that cosine squared of theta x plus cosine squared of theta y plus cosine squared of theta z is equal to what? So we should have to satisfy this equation for determining the direction cosine of the force. Now, if an angle is more than 90 degrees, the cosine is negative, indicating that the sense of the component is opposite to the positive direction of the coordinate axis. Okay, so let's now proceed to Cartesian vectors. Now, the analysis of some problems in three-dimensional force system is simplified using vector algebra. Okay, so you are already with vector algebra. How to add a vector in which the forces are represented in the Cartesian vector form. Now, you try to take note in here now that the right-handed coordinate system is used in the theory of vector algebra. So we have a rectangular or Cartesian coordinate system is said to be right-handed if the thumb of the right hand points in the direction of the positive z-axis. Okay, so if this one in here is now the z-axis, you have now your x-axis and you have your y-axis. So if it curl and it is in the direction of the y-axis, then that is positive. Okay, or it is okay, so it is or from directed. Okay, so when the right hand fingers are curled about the x, directed from the positive x to the positive y-axis. So if this is your x-axis, so if it is directed, so it is now going. Okay, so if this is now your x-axis, okay, you curl. Okay, and if that is the positive x-axis, so if you are going to curl it in that manner, then that vector in there is positive. So let's proceed to a unit vector. From the word unit, so this is a vector of magnitude 1 unit, and this is dimensionless. Okay, which is the same direction in as the vector. So if you have a unit vector, and let us try to consider that the vector is A. So this is written, supposed to be in the bold-faced letter. So the vector A, a unit vector, is equal to the vector A, divide this one by the magnitude of that vector, which is now equal to A. So this one in here is the vector, that is now the first, and this one is now the magnitude of the vector. Okay, so that is now the magnitude of the vector. Now, so what is a Cartesian unit vectors? Okay, because we told before that your vector in the three-dimensional force system okay, could be used, Cartesian vector could be used to simplify our equation in the three-dimensional force system. So we have your Cartesian. Okay, so this is your Cartesian unit vector. Now, so we have now your Cartesian unit vector. So let us try to consider that this is the coordinate axis. Okay, so we now have the coordinate axis. So this is now the x-axis, this is the y-axis, and this one is now the z-axis. Now, so your unit vector, okay, are directed in the positive direction of the coordinate axis. Now, the unit vector corresponding to the z-axis is now a unit vector, so that is I. And the unit vector corresponding to the y-axis is now your j. And the unit vector corresponding to the z-axis is now a unit vector, which is equal to k. You try to take note that these unit vectors are directed in the positive direction of the coordinate axis. Okay, let us now proceed to Cartesian vector representation. Now, using the properties of vector addition, a vector A can be written as the sum of its three components. Okay, so if you have a vector A, so this is now the vector A. So it is written as the sum of its rectangular components. So we have now your AX, multiply this one by I, plus we now have your AY, multiply this one by J, plus AZ, multiply this one by K. So vector A is now equivalent. It has the rectangular components as AXI, AYJ, and AZK. Now you try to take note in here now that your AX in here is, your AX is the magnitude. Okay, magnitude of the vector A in. Okay, so your AX is the magnitude of the vector A in the x direction. And your AY is now the magnitude. So that is the component. When we're speaking of the magnitude of A, so that is the component. Okay, so that is the magnitude of the vector A in the y direction. And your AZ in here is therefore the magnitude of the vector A in the z direction. Okay, you try to take note in here now that if AX is multiplied by a unit vector I, then that is now a vector. Because a unit vector, as what we have defined before, is having a magnitude of one unit. Similarly, if this is the magnitude of the component of A in the y direction, if multiplied by a unit vector, J, so that will now a vector. Similarly, with your component of the magnitude of the vector A in the z direction, when multiplied by K, it will now become a vector. So in other words, the Cartesian form of representing a vector F, so this vector F written in a bold face. Okay, this is equal to f. We now have your cosine of theta x, that is now a unit vector, plus f cosine of theta y, and then we now have a unit vector j. And then plus, we now have your f cosine of theta z. Okay, multiply this one by a unit vector k. So you try to take note in here again that f cosine of theta x is equal to f of x. And your f cosine of theta y is equal to f of y. And your f cosine of theta z is equal to f sub z. So in other words, to represent the vector in its Cartesian form, your f is now equal to f of x, that is now your I, plus f of y, and then we now have your j, plus f sub z, you now have with your k. We now have your k. And this is therefore known as the standard Cartesian form of representing a vector. So we now have your position vectors. Position vector, it is defined as a fixed vector which locates a point in the space relative to another point. So let us try to consider a position vector R. So this position vector R that will extend from the origin of the coordinate axis, that is the position vector R, to any point P whose coordinates are x, y, and z. So that is now the position vector R. It's designated by R. So in Cartesian form, your position vector R is now equal to, so you have now your x minus 0, so that is xi, then plus y minus origin, so you have yj, and then plus zk. So that is therefore your position vector, which is equal to R. Now, for a position vector, so let us try to consider another one in here. So this is, again, the x-axis, this is the y-axis. This one in here is the x-axis, and this one is now your z-axis. Now, let us try to consider a position vector R. So this is now the position vector, and that position vector is now originating from point A. There is now your point A, whose coordinates are xa. We now have ya and za that extend to point B. And the coordinate of point B, we have now your x sub B, we have your y sub B, and we now have your z B. Now, so that your position vector R, so your position vector R is now equal to, so the position vector R is now equal to the tip of the vector minus the tail of the vector. So that is now your xa minus xb minus xa, and then we now have your I. And then we now have plus yb minus ya, and then we have the unit vector j, plus we have your zb minus ZA, and then we now have your K. So that is the position vector R. If a position vector is introduced from the origin to the tail of that position vector, I'm just going to consider that this is now a position vector R sub A. And this one in here is now your position vector R sub B. So that's now your position vector R sub B. So that the position vector RA plus the position vector R is now equal to RB, or that is now position vector B. You try to recall your vector addition. Okay, so you have your vector addition before. So that your R in here is now equal to R sub B, position vector R sub B minus the position vector R sub A. And therefore, the position vector R is now equal to, so your RB is now equal to X sub B I. That is X sub B minus, that is the origin, minus 0. So X sub B minus 0 is X sub B. Okay. And then we now have your I. And then YB minus 0 plus Y sub BJ. And then we have ZB minus 0 plus ZBK. And then we have 2 minus your RA, which is XA minus 0. So that is XA. So we now have X of A, we have I, plus Y sub A, and then we now have your J plus Z sub A, we now have your K. Okay, so these are now your position vectors. So you try to take note in here now that your I, J, and K components of the position vector may be formed by taking the coordinate of the tail of the vector and subtracting them from the corresponding coordinates of the head of the vector. So this means to say that when you are getting a unit vector, the components of the unit vector, okay, the components in the X, in the Y, and in the Z should be the head of the vector minus the tail of the vector. So that is the head of the vector minus the tail of the vector. Now, so for your R sub B, that is the head of the vector minus the tail of the vector. And this one in here, this is the head of the vector minus the tail of the vector. Force vector along a line. Okay, let us try to consider a vector directed from point A to point B. So this is a vector F which is directed from point A to point B. Now the coordinates of point A are X of A, so we have Y sub A and Z sub A. And the coordinates of point B, we have X sub B, Y sub B, and then we now have Z sub B. So this vector F, if you can be expressed as a Cartesian vector by realizing that it has the same direction and sense as a position vector R acting along its line of action. So acting along its line of action. So let us try to. So if you try to get this one in here now, your vector f, okay, so the vector f is now equal to the magnitude of this vector multiply this one by a unit vector. So let's try to multiply this one by a unit vector. And we define a unit vector, okay, is now equal to. So at this point, I will now going to introduce a position vector along the line of action of the vector f. So this is now your position vector, and that is now your vector r. So the position vector, therefore, is now equal to the vector position vector. The unit vector is now equal to the position vector. So that is the position vector r divided by the magnitude of that position vector. Let's try to multiply this, divide this by the magnitude of the position vector. So in other words, this is now the vector f is now equal to the magnitude of that vector multiply this one by a unit vector, which is r, all over now your r, which is now the magnitude of that vector. So your position vector, okay, so your r is now your position vector. R is now equal to, so we have xb minus the tail xa, and then we now have your I plus the head yb minus the tail ya, and then we have j plus we have zb minus the tail za, and that is now your k. So that is therefore the position vector. So let us try to get now the magnitude of this position vector. So what is therefore the distance from point A to point B? Okay, so we have the distance, okay, from point A, so that is point A to point B. Okay, so the distance from point A to point B, which is now the magnitude of R. So that is now the magnitude of R. Okay, so we have the magnitude of R, so that is the magnitude. So we now have the square root of xb minus x of a square plus yb minus ya square plus zb minus za square. So if you try to get now the vector f in its standard Cartesian form, so the vector f in its standard Cartesian form is now equal to, so we now have the magnitude of this vector, and then multiply this one by the position vector xb minus xa, so we now have your I plus yb minus ya, and this is now your j plus we have zb minus za, and then k, all over the magnitude of that position vector, which is therefore the square root of xb minus xa a square plus we have yb minus ya square plus we have zb minus za square.